Good morning, guys. So it's Sunday, and we're going to continue. I hope you guys enjoyed the keynote this morning. How many of you were there? Yeah. All right. So we're going to continue, and I'm really, this one's the easiest introduction I get to do because I work with Patrick, and I work at Facebook, and so I already can, I didn't have to like read or ask him how to pronounce his name or anything. Shuff, yes. It's a shell archive. Mm-hmm. So anyway, Patrick's going to be talking about how we do load balancing at Facebook, and one of the things we recently open sourced. It's a really cool talk, and I hope you guys enjoy. So without further ado.
Cool. Thanks, Phil. So yes, this talk is building a billion-user load balancer. My name is Patrick Shuff, and I work on the traffic team at Facebook. A little bit about me. I've got a BS in CSE from Ohio State. I joined Facebook in late 2012, and I worked on the site reliability team for a little while, and then I had an opportunity last year to move to one of the teams that was most interesting to me, traffic. And some of my favorite things in order, and Jimmy already knows this, Linux, Python, Emacs, and Git. So when people ask me what it means to be on the traffic team, or what does the traffic team actually do, this is the picture that comes to mind. This is a picture of all the users on Facebook everywhere in the world and all the connections that they have to other people. The role of the traffic team is to make sure that all of these people, when they whip out their phone and go to the Facebook app or they go to Facebook on their website, is to make sure that all the packets, all the requests that they make get to our servers as quickly and efficiently as possible. So that's kind of the TLDR of what the traffic team does. So just to go over the agenda for today, we're going to start off by talking about how we serve dynamic Facebook requests dynamic Facebook requests. We're going to dig a little bit into load balancing, layer 4 and layer 7 load balancing. We're going to talk about how we've deployed our edge points of presence around the world to reduce latency. Then we'll lastly talk about our global load balancing, our DNS server called Cartography. And then actually lastly, we'll talk about some of the different open source components that actually make up our global load balancing system. So just to kind of talk a little bit about what is Facebook. All the requests that come into Facebook are mainly broken out into two different categories. So one is dynamic requests. So those are requests that are actually going to hit a HHVM, which is our hip-hop virtual machine, which runs all of our PHP and hack code. These are requests that are going to generate your news feed when you like something, when you create a status update. All those are actually going to hit a web server, do a whole bunch of things, maybe branch off into tens, if not many tens of services on the back end, and then it's going to send a request back to you. The other half of this, of the Facebook requests, are static resources. These are resources or requests that aren't going to change each time you hit them. So very common ones are images, videos, and then of course JavaScript and CSS. So here's a weekly cycle of what Facebook's egress looks like. And when I say egress, I mean all the bits per second that are leaving Facebook. And we have this diurnal cycle, which means it's a fancy way of saying a cycle that repeats itself after 24 hours. This is a full week of the Facebook traffic patterns. So this is egress. These are bits leaving our border routers, leaving the Facebook network and going onto the internet. This is our ingress. So these are all bits coming in. So these are the requests that we actually are taking, doing something with, and then returning back. So you can see that we're egressing a lot more bits than we're taking in. Here's the typical egress pattern for a single day. So we kind of have this double, it kind of ramps up. This is about 11 a.m. here. Then we peak about 3 p.m.-ish. And then we kind of have this, yes, good question. This is Pacific time zone, yeah. So Pacific time zone here. And then we kind of have this about 6 or 7 p.m., we kind of have this other hump here. And what this actually represents is the sum of all the time zones in the world. So each time zone has its own kind of curve like this. So this graph here is the sum of all time zones in the world. So this red one's Canada, this one's the UK, so Europe, Indonesia. So every region has its own kind of unique pattern. Cool. So some cool traffic stats. We released our yearly numbers earlier this month, and as of the end of December 2014, we had 1.3 million people per month actively using Facebook. And as of December 2014, on average, during the month of December, there were 890 million people using Facebook. So when I see these numbers, like, these are great, you know, Facebook's continuing to grow, but I'm also thinking as a traffic engineer, like, wow, we're gonna, you know, we're serving terabits of egress, and these numbers keep going up. You know, we have hundreds of millions of TCP connections at peak connected to devices around the world, and we have tens of millions of actual requests coming in every second. So cool. Somebody asked me before I was doing this talk, how technical is it going to be? And my answer, I want my answer to be as technical as you guys want it to be. We're going to talk about TCP and IP. I think it's reasonably technical, but I want you guys, if you have any questions, if we're not going deep enough, let me know, and I'll try to go as deep as we can. So if I'm just covering something too high level, let me know. So OSI model, you have 7 layers of the OSI model. The important things the 3 layers that we're gonna look at today are layer 7, the application level. We serve HTTP and Speedy from Facebook. We're only gonna focus on HTTP today. We're also gonna talk a bit about layer 4, transport layer. All of the requests that come into Facebook outside of DNS requests are gonna be TCP. So we'll talk about how we do that, TCP load balancing. And then we'll talk a bit about layer 3, so Internet Protocol IP routing. Here's an example of the IP header. So there's a lot of different bits up here that aren't going to be that important for this talk. The important things to know about the IP layer 3 header is the source address and destination address. Here's the TCP header. A lot of different information down here, which is normally important as a traffic engineer, but for the purpose of this talk, we're only going to care about the source port and destination port in TCP. And here's an example of an HTTP request. So it's a very simple get to facebook.com. So when you're actually sending a request to Facebook, you know, these are all different layers as we're actually sending the request. So you have your HTTP request, which is encapsulated inside of a TCP segment, which is encapsulated inside of an IP packet. So just kind of keep that in mind as we talk about these different load balancing techniques. So putting it all together, this is kind of hard to see and understand what's going on. So I'm kind of going to generalize it and just show this throughout the rest of the talk to talk about the different layers that a request traverses. So how do we serve dynamic Facebook requests? So the first part of this talk is how we is only going to be how these things, how requests are served inside the data center. We'll talk about how we serve it outside of the data center a little bit later. Today we have 5 different data centers, 4 in North America and the United States, and 1's in Luleå, Sweden. So typical Facebook request, you pull out your phone, you pull up the Facebook app. The first thing it's going to do is, what is facebook.com? And then you're going to hit one of our DNS servers, and then we're going to return you an A record, and we're just going to assume IPv4 for now. And then it's going to go out to that IP address and hit one of our servers. So this is an example if we didn't have any load balancing and every Facebook request was going to hit one web server. So the problem here is compared to all the requests, our web server can only do a very low amount of RPS. So this is a big problem. There's also other problems in that you would have to terminate TCP on this server and also do SSL negotiation, which there's actually non-trivial, there's non-zero overhead for actually doing that. So how do we get more RPS? We add a load balancer. So ProxyGens are our layer 7 load balancer, and when your request comes into Facebook, it's going to hit this layer 7 load balancer. It's going to terminate TCP and SSL, and then that reverse proxy, or ProxyGens is a reverse proxy, it's going to reverse proxy that back to the web server, or one of the web servers to be whatever dynamic content you want generated, and then ProxyGen is going to send that back to the user. So this is great. But we need to be able to scale out to a bunch of ProxyGens so that we can scale out to a bunch of web servers behind that ProxyGen. So we add another load balancer. So our layer 4 load balancer is Shiv. It's based on the open source IPPS module, which means IP virtual server. And when your packet comes into Facebook, it's going to hit this layer 4 load balancer, and it's going to get consistently hashed to one of these ProxyGen boxes. So it's going to take the source destination source IP, destination IP, sorry, source IP, destination source port, destination IP, destination port. It's going to consistently hash that, and that's going to route that to ProxyGen. So it's really like a TCP router. So this is great. How do we get more RPS? We can't serve all the Facebook just with this. We had another load balancer. So, the last load balancer, at least within the cluster, is actually our top of rack switch. We do layer 3 from our top of racks throughout the rest of our network. So the only layer 2 is within the network. And the way this works, and we'll talk about it in a little more detail, is we'll talk about it in a little more detail in a little bit. But the router on the top of the rack does ECMPs, which means equal cost multipathing. It equal cost multipaths the packets to the Shiv server, and it is a flow-based equal cost multipathing, so it should go to the same Shiv server every time. Cool. So this is great. This is what a typical front-end cluster looks like. We'll have some tens of Shivs, 10 IPPS servers, all with ECMP. And then we'll have many hundreds of Proxy Gens behind that terminating TCP and SSL. And then we'll have many, many thousands of actual HHVM web servers that are actually doing the meat of the request processing. So cool. So we have a lot. We can do a lot of RPS with this cluster, but we need redundancy and we need to process even more requests. So what do? Is we add another one of those.
Turtles all the way there.
So this is awesome. So we have, this is our unit of, so we have our front end cluster there, that's a unit. Now we have a data center, which is a bunch of clusters. So we have a bunch of clusters, we have a data center. How do we get more RPS out of this? We add another data center. So this is kind of the last piece of, how we actually scale out physically the footprint of all the web servers around in the 5 data centers that I had showed before. So one of the important things to note here is in all the diagrams, you've kind of seen this top-down approach. You have the L4 load balancer, L7 load balancer, the web server in the back end doing the dynamic request. It's not actually like that in practice. So we do have a way that these servers, we use it's kind of like Mesos, if you guys are familiar with that. It's a way that we can schedule out these tasks or these processes to run wherever. We don't really care where they run as long as they run somewhere. So in practice, our layer 4 load balancer is going to live in this, it could live in the same rack as our L7 load balancer all around a whole bunch of web servers. Cool. Any questions so far? Yeah.
What's the load balancing algorithms that you guys use from the Proxy Gens to HHVM boxes? Is that also IP hashing, or do you do round robin?
There's some, it's not, I think we do some interesting stuff there. And it's hard to explain. We do some different hashing algorithms based on okay, so within a cluster, I don't think we do anything. Based on what actual data center will route you to, we might do that where more of your friends are actually there. So we have the kind of a social hash that we can hash. But sorry, within a cluster, I think we do hash just to any web server to do the. We don't pin requests or any users to any web HHVM instance. Cool. All right. So now let's kind of dig in. Yes.
Is there any specific hardware on the layer 4 where there's the routing? It's all just software?
Yeah. So it's commodity hardware. So these are x86 boxes. That's a good question. The reason why we kind of have this why we kind of have this approach is this is all commodity hardware and it can fail at any time. So this Shiv box could go away, and we're going to talk about failure scenarios in a little bit, but it's just going to get scheduled somewhere else. So this is all commodity, in many cases, open compute hardware that fails. So.
Do you guys write your own scheduler?
So
You're not running Mesos.
no, yeah, we do have our own scheduler, and I think there is a talk on SlideShare. It's called Tupperware, and one of the folks from the Tupperware team had given a talk about it. So it's pretty interesting. But it's very similar like Mesos. We've had it for a couple years now, though. Yeah.
Are these bare metal containers or virtualization?
No, we don't do any virtualization in production. Everything's bare metal. Yep. So we do roots, LXC, yeah, all bare metal. Yeah. There's a whole bunch of load balancing. Once you hit the actual HHVM server, I mentioned before, it could hit tens, if not 100 different services on your request. We're sharding everywhere. Everything is sharded. There's a whole bunch of load balancing going on behind the actual HHVM. This talk is really just how your packets get from your phone to one of our servers. Yeah. Nope, HTTPS. Yep. Sorry, HTTP. Yes, correct. Yeah, we're actually just proxying, so it is an encrypted connection. But we're just proxying those requests back to the HHVM server. Yep.
From HHVM, you do direct server response back and avoid the proxy, or?
Yep. Yeah, we'll get to that. There's a slide on that. Good question. SSL happens at ProxyGen at L7. So L4 load balancer is doing the TCP routing to make sure we keep those TCP connections alive. And then we terminate TCP and SSL right here. Where's the session? It's happening all right here. Yeah. Cool. Good question, though. Excellent. Yeah. We'll get to it. Yep, we'll talk about it. Cool. So let's dig into the L4 and L7 load balancing a little bit. So to break it down, you've already seen this ECMP to our L4 load balancer. That gets consistently hashed to one of our ProxyGen servers, terminates TCP and SSL, and then that gets proxied back to an HHVM. So we saw our OSI model before. So the L7 load balancer is ProxyGen, L4 load balancer is Shiv, and then we have ECMP in there as well. So I mentioned before, these L4 load balancers, they get ECMP'd from the top of rack. And the way that works is we use ExaBGP, which is a really easy Python BGP daemon, to peer with our top of rack server. So this basically says, I have this IP address. This guy says, I have this IP address. It's all the same IP address. So that's how our ECMP, that's how it gets, we tell the switch, where we actually have this IP address, so it gets routed to us. And then from there, once the packet comes in, it gets inspected by IPPS, and then again, it's consistently hashed based on source and destination port and IP, and then it gets proxied down to an L7 load balancer. So one of the important things here is we actually do keep state in the L4 load balancer in IPPS. So, and we'll talk about a failure scenario in a little bit and why that's really important. So here's an example request. Client comes in, L4 load balancer. It gets consistently hashed to this L7 load balancer. Another user comes in, L4 load balancer, gets consistently hashed to this L7 load balancer. So what happens when this Shiv box goes away? For one, it'll be rescheduled, but it might not happen immediately. So what's going to happen is that other user's request is going to come in, still on the same TCP session, still in a connected state, and it's going to get routed back to the same server. Since we are using a consistent hash based on source IP and port, as long as these two Shiv servers have the exact same state of the world in terms of the healthy servers underneath it, it will get consistently hashed and you don't have to reconnect TCP, which is really important. So let's look at another example. We lose a ProxyGen server. We lose an L7 load balancer. So the request comes in, that server's not healthy. So it's going to get routed to the next one. It's not necessarily the one beside it, but it's going to get consistently hashed to another L7 load balancer. So say that server becomes healthy again, and then the next TCP segment comes in. It's going to hit our L4 load balancer. It's not going to go back to the original one. Since we do keep state in IPPS, it will remember that it should have gone to this previous L7 load balancer. So we don't have to we don't break our TCP connection. We're not sending a reset back to the client. Cool. Yeah, that's something that IPPS does. Yeah. So I should kind of explain the two. So IPPS is the kernel module that's actually doing the load balancing. Shiv is kind of our Python on top of IPPS that's kind of doing the health checking and all that. So that's a core IPPS thing. Yeah. What's that? Okay, cool. That's awesome. I love seeing more folks using IPPS. It's great. Cool, so direct server return. Somebody asked about this a little bit ago. It's actually really important. We're only focusing on dynamic requests today, But in static requests, direct server return is really important, and I'll explain why in a second. So the way this actually works, we kind of cheated a little bit in the previous slides. When your packet comes in, hits the L4 load balancer, TCP and SSL are terminated on the L7 load balancer. When that packet egresses, when it leaves the ProxyGen server, it actually does not go back through the layer 4 load balancer. It actually goes directly back to the client, so out through our routers, back to the internet, back to the client. So the way this works is this is the original IP packet that we had. So IP, TCP, HTTP requests. This is what happens when it actually gets to the IPVS server. So IPVS gets the packet, and then it does a consistent hashing, and it determines what ProxyGen server it should actually go to. And then what it does is it encapsulates that in another IPN packet. So we're doing IP and IP encapsulation. So at that point, that packet will be, the destination will be the ProxyGen server. So then it gets to the ProxyGen server, and then the ProxyGen decapsulates it. So it says, yes, this IP packet's for me. And it's like, cool. And then it takes it inside, it's like, okay, this is IP and IP encapsulation. It just drops that back on the network stack, and then it serves the request like normal. And at that point, it just egresses, because it's the original IP packet at that point, it just egresses back to the user that way. Cool.
How does that look on the server? Is it a custom bridge or something?
So we have a tunnel interface on the server. So yeah, that's a good point. I was thinking about putting that in here, but I didn't. Good question though. So we actually have a tunnel interface on there where that IP is actually living. So these guys don't respond to the IP they're serving requests for on the link, but they do in that tunnel interface. Good question. Cool. Yeah. Correct. Yeah. Yep. Everything's done on TCP or on the L7 load balancer. Yep. Yeah. We used to do L2 DSR. So instead of doing the IP and IP encapsulation, so the question was, usually I see people just rewriting MAC addresses on the IP header, or sorry, on the frame, the Ethernet frame, right? We used to do that, but we can't do that because we're layer 3 on the top of rack. So as we've moved completely to layer 3 clusters, we don't have the layer 2 clusters anymore. We just do the IP and IP encapsulation instead of rewriting the destination MAC address. Right. Yeah. It wouldn't route out of our top of rack. Yeah. Yeah. Cool. Good question though. Okay. So just to kind of break down DSR a little bit, you're on your phone, your packet's coming in, it hits Shiv, and then Shiv takes that packet. It determines what ProxyGen server it should actually be destined for. Then it puts another IP packet around it with the destination being that ProxyGen server. ProxyGen gets it, looks at the IP packet, says, this is mine. It sees there's an IP packet on the inside, drops it back on the networking stack. The tunnel interface picks it up, and then that's what ProxyGen's listening on, is that IP address on the tunnel interface. Then it proxies that back to HHVM, and then that IP, that response will be going directly back to the client. Cool. Any other questions there? No, multiple. Well, it depends. So those Shiv boxes float around. So I know that we've run into an issue where we couldn't have. There's a very small number of ECMP that was reliable on the plethora of hardware that we're using. So we have a couple. It's less than, I think, like 16 generally. But in general, you're not going to have a bunch of Shivs in one rack. You want those spread out across a bunch of racks. So it's probably not. It's probably just like 1 or 2 per rack. Cool. So now we're going to talk about our edge POPs. POP means point of presence, and how this actually helps us reduce latency. So in late 2011, all of our we did a study and to see what kind of round trip time, what kind of latency we were seeing from clients all around the world. And as you can see here, white is good, red is bad. In North America, Facebook experience was pretty darn good, but outside of the United States, or outside of North America, it wasn't that great. So what we did is we wanted to reduce the amount of work that these clients had to do and reduce the amount of distance that these packets had to travel. So here's an example between Seoul and our Prineville, Oregon data center. There's about 75 milliseconds of latency between the two. And to actually just connect, just to establish this TCP session, it would take over 150 milliseconds. So you have your TCP three-way handshake, SYN, SYN-ACK, ACK. Those both have to traverse 75 seconds, so there's 150 milliseconds just in TCP connection. Then you have to factor in the five-way SSL handshake. So that adds another 300 milliseconds to the time it takes to establish a connection. And then after 600 seconds, you finally get your first HTTP request. And that's a real bummer. It's a long time. So what we decided to do was we actually wanted to put servers closer to the clients that are going to connect to Facebook. So in this case, we put an edge POP, a point of presence, in Tokyo. And for the users from Seoul that are trying to get to Facebook, we would just send them directly to that edge POP. So here's the same example where they only established TCP and SSL to Tokyo, which is about 15 milliseconds away. Instead of 450 milliseconds, you have 90 milliseconds. So there's your session. And then from there, to actually do your HTTP request, or your dynamic request, it will actually traverse all the way back. But the nice thing here, and as I mentioned a little bit before the talk, we want to get these packets off the internet as fast as possible. We have pre-established connections, HTTPS connections between our edge and Facebook, so we don't have to worry about that time. And we also, can do a lot of TCP tuning. So we don't have to worry about the TCP on the client side. We can do all this TCP optimizations right here to make this as quickly and as low latent as possible. Yeah. It's mostly, we have our own backbone infrastructure. Yeah. Yeah, it's dedicated transit. Yeah. Cool. So instead of 600 milliseconds to receive an HTTP response by deploying edge locations around the world closer to the clients using Facebook, we've reduced it over half. So instead of 600 milliseconds, it takes only 240. So this was obviously a big win. Here's a map of all the different edge POP locations around the world. We're deploying more and more as fast as we can. So there's definitely a lot of places that we still haven't been, but we're moving as quickly as possible on these. So how do the load balancers and the POP actually work? Here's an example in Germany. So here's an example of a user in Germany that's going to Facebook. So their packet comes in, it goes through the top of rack switch, it gets ECMP'd to one of the L4 load balancers. This might look familiar. Then it gets consistently hashed to one of our L7 proxies, so TCP and SSL happen in the POP. The only difference between the POP and the data centers is we don't have the big web servers that are serving the dynamic content. So what happens is that connection gets proxied back on an optimized TCP HTTPS session back to our data center. Goes through the exact same thing. The load balancing and the POPs are the exact same as the data center minus HHVM. Cool. So now let's talk about how we actually decide how the people using Facebook get sent to the edge locations. And that's our DNS load balancer called Cartographer. So again, here's our edge locations around the world. We have 1.39 billion people every month using Facebook. And we need to figure out the most optimal way for them to actually get to the nearest edge location to serve their requests. So Cartographer takes a lot of different pieces of information into consideration. One of the most important ones is how close is the edge location to that user. Distance doesn't always mean, closeness doesn't always mean physical distance. You'd be surprised how your packets get routed around the internet. Do a trace route or an MTR sometime and just watch it. It's pretty fun. So we have to figure out what does it really mean to be close to one of our POPs or one of our edge locations, and also capacity. We're not deploying data centers in these countries. We're deploying a couple racks of servers, and they have finite resources. They have finite CPU. They have finite memory, and also network capacity. And network capacity goes down. Some of our POPs are more flaky than others, so we need to take that into consideration so we just don't crush these POPs. So the way we measure closeness is with a strategy called Sonar. And the way this works is we do a very small sampling, one in every very high number of requests, of static resource requests will actually get sent to not the most optimal POP. So we will send that and grab that photo from some other POP around the world. And we have a ton of traffic. So even though we're doing a very, very tiny percentage of this, it actually generates enough data that it gives us a really good idea of how the world is mapped. So we have a pretty good, it gives us a lot of data to figure out what ISPs or what net blocks should go to the most optimal POP. The way Cartographer works is it kind of takes in a bunch of different information. I already mentioned capacity, resolvers and latency based on the ISP or the DNS resolver that actually requested the DNS from us. We measure that. Also just routing. Maybe we have some down paths. Maybe we have a backbone fiber cut for whatever reason and we don't have enough capacity there. And of course just the health of the POP. Maybe we deployed a new version on one POP and it's just not serving requests. It's throwing back 500s. So all these things are taken into consideration. They're all processed in Cartographer. And that's what generates this kind of static map of the internet and how we should serve requests. And then from there, we upload that into our DNS server. This happens every couple minutes. This is something that happens very frequently. And we just use tiny DNS as our DNS resolver. And then from there, all the requests that comes in, we do a lookup based on the IP net block that they're in, and then we serve the optimal POP location that way. So here's an example of Cartographer. So we have all those pieces that I just mentioned. DNS map is generated, gets thrown into tiny DNS, and then here's all the different ISP resolvers that are actually hitting it. Cool. So here's Cartographer in action. This graph here shows this line, this red orangish line, shows the actual user demand that should go to this POP. So it should go to this edge location. Sorry, that could go to this edge location. That's eligible too. But here is the capacity line. This is what we say, this is all that can actually go to it. So this is what could go to it if we didn't have Cartographer. And this is what actually is going to it. So this jagged line here is showing that we're like rate limiting the RPS. This is requests per second per POP right here. So we're doing a very good job of keeping it very close to the actual capacity. And then here's the trough here. So this is when everybody goes to sleep. Here's another graph showing a regional load shed. So this could be all the POPs in Europe. So everybody's sleeping. People are waking up. And then this shows the different time zones based on the POP. Everything is kind of time shifted in some way. So this shows all the POPs in that region and then the capacity line right there. And here's an even more crazy graph is our global load shedding. So this is what it would look like for every POP that we have at Facebook, and then our capacity limit there. So I think there are a lot more lines now than the way this used to be. Cool. So with that, I'd like to talk about some of the different open source contributions. ProxyGen is something we released at the end of last year. Sorry, the HTTP parsing libraries. So we've released the very core the libraries that we do all of our HTTP and speedy processing. So those are available on GitHub if you're interested in building your own web server or load balancer. TinyDNS, DJB built that, open source. IPPS that we've talked about a lot, it's kind of our workhorse. It is a kernel module, so they have really nice command line tools as well for actually modifying it. XCBGP that we use on Shiv to actually BGP peer to from the Shiv box to our top of rack. And then Python is the glue that holds Facebook together. So I thought I'd throw that on here too. We have a lot of stuff in Python. Cool. So, all right, question. That's a good question. I'm not sure. Okay. I'm not sure, yeah. We've been using TinyDNS for a little bit. I'll have to look into that though. Cool. So TLDL, if you fell asleep during this too long, didn't listen, I'll kind of give a recap. We have edge pops around the world. If you're on your phone anywhere in the world, you're going to go to an edge pop. We're going to terminate TCP and SSL, hopefully in a very optimal place to where you are physically, or maybe not physically, but how the IPs actually get to you. The request is going to get proxied back to an origin data center. HHVM is going to process the request, and then it's going to get back to you. DSR, direct server return. Packets come in through our L4 load balancer. TCP and SSL request, and it actually egresses directly back to the clients. Our three primary load balancers, Cartography is our DNS-based load balancer. TCP is Shiv and IPPS. HTTP and Speedy is our ProxyGen reverse proxy. And that is it. Any questions? Yeah. Totally, yeah. So, yes, so I think if you dig facebook.com, somebody do that. I think it's 5 minutes is our TTL. It's totally a problem. If we lose a POP, it's going to take 5 minutes for that TTL, for that record to propagate out to the internet. So there's always going to be at least some time there. There's not much we can do that because we are based on, the internet runs on DNS. So yeah, there's always going to be a little bit of period there where there might be requests that aren't getting fulfilled. The other thing that is actually a problem is people don't respect TTLs. So people will hard code IP addresses, and when you drain that edge POP or you drain that data center, they're screwed. And it's, they're hitting API.facebook.com and it's breaking. So don't hard code IP addresses. Another interesting thing is if you use open resolvers, if you use like an open Google DNS resolver, you're kind of, in a way, you're not getting the most optimal return, because we see the Google DNS resolver, because that factors into where we actually send you. So you might not always get sent to the optimal POP location as well. Yeah, good question. I was wondering if anybody was going to ask me about that. We don't do any cast TCP anywhere at Facebook. We do any cast UDP for DNS. That's the only place we do it. Yeah. We just don't want the load balancing. So the question was, do we do any cast at Facebook? The reason why we don't is we don't want the load balancing decisions being based on a bunch of routers that get BGP routes. We could crush like POPs very easily if somebody makes a bad decision on how to route our traffic. We want to have full control of how we actually get routed, and we do that with Layer 7. Another interesting thing is you mentioned DNS, how we actually load balance. For a lot of our static resources, since we're generating the URLs inside the PHP code, those actually will fail over a lot quicker. We don't use DNS for those. We actually send a URL for a very specific POP. We didn't talk about CDN in this talk, any static resources, but those we'll send if that drain is popped, or if that POP is drained, we'll very quickly fail that over and send them to some other location, or we'll send them to a generic URL that will just get resolved somewhere. Based on the other DNS optimal like POP thing. Yeah. Cool. Does that answer your question? I didn't answer why. There's kind of internal. Well, I did answer kind of BGP. Nobody's just taking the time to do it, I think. I think there might be some use cases where anycast TCP might be good. But one of the biggest downsides is maybe you have an ISP that decides this packet should go this way, this packet should go this way, and we don't have any control over that. So you're like never going to establish TCP if they send one to this POP and one to this POP. So that's one of the big downsides is there's going to be problems way downstream that we're never even going to see, because it's a really tiny ISP that's making poor decisions on their routers. Yeah.
You said your POP is where you terminate SSL. So in that case, you're running a bunch of proxy gens in the POP?
Yeah. Correct. Yep. ProxyGen is Layer 4 load balancer and Layer 7. The only difference between that and the data center is we don't have the web servers actually serving the dynamic requests.
So the ProxyGen just sends the request to the real server?
Yep. Yeah, we have pre-established HTTPS connections back to the real, ProxyGen's back in our origin data centers, so they all go over that, over an optimized TCP connection.
So that's another layer of proxy?
Yeah, yeah. I think there was a slide on that. But yeah, it's the exact same thing. Yeah, a lot of proxying. We love the proxy and load balance. Yeah.
Any reason not to send the DNS TTL to like 50 instead of 300?
Yeah, I think we'd piss a lot of people off if we did that. That's not a. like we do a ton of DNS requests, and I know there's even been cases where ISPs are like, we don't want to do 5 minutes. Like that's like their resolvers are getting crushed. So that's not like an authoritative answer, but yeah, 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 yeah. You can talk to me after this if you want for a deeper dive. We'll make this available. Yeah, yeah, yeah.
All the L7 load balancers are behind all of the L4 load balancers, right? Many to many.
Correct.
What about L7 to web servers? Is there like a dedicated pool of web servers for each load balancer, or do they all go to any web servers?
Yep. So I'll answer the question over there and this question with the slide right here. So this is a POP. This is a POP in, well, it could be anywhere. France. Let's say France, because it's kind of by Germany. So the request comes in to the POP, layer 4, TCP and SSL right here. And then from there, since we don't have, these are the web servers that we're talking about, the HHVM. So we don't have these in the POPs. So that request is going to get proxied back to Facebook origin data center, United States, maybe Luleå, Sweden. And then it's going to go through the exact same load balancing to a real web server that can actually process the request. The IP and IP encapsulation, it happens between here and here. So IP and IP encapsulation, I think I have a slide on that somewhere. Yeah, it happens only between the L4 load balancer and the L7. Once L7 gets it, it takes the request and then sends it where it needs to go.
It happens twice for that connection, right?
Correct.
But the second L7 doesn't, the second L7 then sends back to the first L7?
Yes, yeah, it will flow back through that first L7, correct. Yeah. Yeah. Oh, sorry, what was your question? Say it again, please.
So no matter which layer 4 load balancer it gets routed to, it will get routed to the same layer 7, correct?
Correct.
Between the L7 and the web servers, can it route from, like, does each L7 have a dedicated
No.
web servers that it forwards to, or they all go to any?
Yeah, good so that's all within the cluster. So I mentioned we have the concept of a cluster. So let me just flip back to that slide real quick. So the request is going to come in. This is a cluster. So these L4 load balancers here, it's going to come in. It's going to depend to, well, sorry, that flow, that TCP session is going to stay on the same load balancer. And then there's like hundreds of or thousands of those HHVM web servers behind those. And they don't get routed to the same one. It will just send to one of them between the L7 and the actual web servers.
But any L7 can send to any web
Yes, correct. Yeah. Yep. Yeah.
So the final data center doesn't really matter.
Correct.
In that case, I might assume that all the data centers have all the data completely mirrored.
Correct. Yes, yeah. You can hit it. Well, it's not necessarily true that each of them have everything mirrored, but yeah, you can go to any data center, and that HHVM instance will be able to process your request. So it'll go out and hit all the different services behind that needs. No, we have one in Luleå, Sweden. Yeah. Well, the HHVMs are all in our origin data centers, so we have 5 of those. Yeah. Correct. Yep.
So there is data behind.
Correct.
Replicated.
Correct. Well, if it's not replicated, it knows where to go to get it. Yeah. It's HTTP health checks. So these guys are constantly hitting these with HTTP health checks, and then these guys are constantly hitting those with HTTP health checks. Yeah, we have our own service discovery tool, our service discovery based on Zookeeper. So yeah, all these guys know about these through service discovery, and then those guys know about those through service discovery, and it's either enabled or disabled. Yeah. Nope. Nope. It's checking locally. So one of the things we didn't talk about is how we do static resources. We do a lot of caching inside of the POPs. So in many cases where there was actually being proxied back to Facebook, we do aggressive caching in the POPs as well. Yeah, so it's a good question. In many cases, you know, your content might already be, the static resource might already be in that POP. But I didn't include static because I didn't know how we would do on time. Yeah.
So, well, we actually use DNS side. If you ever that's why we don't use it for DNS. And then I just looked up on some using a subtap literalized middle and
Oh, cool. Cool. Good. Nice.
Comment.
Yeah.
You guys are TCL at 9 seconds, so you might have taken into consideration what ISPs are talking to, not flat.
Okay. Oh, interesting. I didn't realize that. I don't know why I had 5 minutes in my mind. Good to know. I'm going to go change that. No, I'm just kidding. Cool. Any other questions? Awesome questions. Oh, yeah. Yeah. So there's a, yeah, it's unfortunate, and there is an interest, well, there is a way you can make that not so painful, and you can actually announce the VIPs from the down pop somewhere else. So that's a strategy that can happen. If that makes sense. Like, so they're unreachable via IP. We can just BGP announce those from some other pop, and that's not a great solution. It's something we've talked about doing.
Java did that as a whole bunch. It was a security feature in a whole bunch of their versions where they statically cached IP lookups,
Nice.
which broke a lot of stuff.
It's a bummer. Yeah, respect your TTLs. Yeah. Yep. Yep. There's a lot of reasons for that. In general, we do a lot of peering with other networks. So it might not go through the public internet. We might peer directly with some other like big ISP. So we don't do any of that in the data centers. So in general, we don't have that. We have that connected through our backbone to a lot of our different POPs, but we don't actually connect it to the public internet per se, at least not to serve production traffic. So yes, even if you're right next to Prineville, Oregon, you're gonna probably get sent to Seattle or something, yeah, which isn't that far away. It's a couple milliseconds. Cool. Any other questions? Yeah. Seconds. Yeah, they're happening very quickly. Yeah. Cool. All right. Yeah. So after I said that, I'm going to take it back. I said that these guys definitely check these. I think we used to do it, and maybe Phil or Casey can correct me. I think we used to have L7, the Proxy Gens hitting all these for health checks. I don't think we do that anymore. I think we have a centralized service that will check all these and then change their service discovery, enabled or disabled. So they'll disable them there. So I think this was just like too much. There's a lot of not a lot of overhead, but there's just a lot of traffic going across the wire for each one of these to connect to all 7,000 of these. So, or 7,000, like many tens of thousands probably. So I think we actually do have a centralized server now. We used to do it this way, that actually enables and disables them. Cool. Yeah. HTTPS. Yep. Yep. Yeah. We have pre-established connections to make sure that we don't have to wait for that TCP and SSL handshake to happen. We've already done it. So, yeah, you just get proxy through the existing connections. Cool. All right. Thanks, everybody.
Great talk, bud.
Thanks, man. Yeah, thanks, guys.